Okay, yes, so the seminar will be in English. So today we are very lucky. We have Daniel Barredo, who is a world-leading expert in Rydberg atoms. So he did the PhD actually here in Madrid, in Autónoma, I think, with Rodolfo Miranda. Then he moved to cold atoms in the group of Tilman Fau, and then to the group of Antoine Broadways. And now we are very lucky, actually, because he just came so it's into CSIC. He's in the Center of Nanoscience, I think it's in Asturias. I don't know, actually, this institute. So hopefully he's mounting his own lab in this Rydberg atomic arrays. And today we'll talk about quantum simulation of spin Hamiltonian with arrays of Rydberg atoms. So whenever you want, Daniel, you can start.
Okay, thank you very much for the introduction. First of all, I would like to take this opportunity to thank Alejandro for inviting me here. In the following minutes, I will be talking about Rydberg atoms, and in particular, I would like to present you our approach to engineer spin Hamiltonians using two-dimensional arrays of single atoms. This work, for now, has been done in Barredo in the group of Antoine Broadways. And for those of you who don't know the group, this is a recent picture of the team working with Rydberg atoms there. You may recognize Antoine and Thierry, who are the permanent members of the team. And most of the results that we'll tell you about today are part of the PhD thesis of Pascal Scholl, with contributions from Anna, Kai, and Guillaume that are also working in the lab. On the theoretical side, we have different collaborations, but recently we had the collaboration of Andreas Loschli in Innsbruck, especially for the theory of the Ising model. And also for the XY model, the quantum simulation, the XY model, we had the help of the group of Hans-Peter Büchler in Stuttgart. As for the motivation for our work, I would say that this is a shared motivation with many people and many of you, because we believe that quantum simulation can help us understand the physics behind complex many-body systems, like, for example, quantum magnets, high-temperature superconductors, or even processes like transport in molecular wires or even biological systems. All the systems that you see here, they have in common that they can be very well described, or at least is what we think now, by simple models, like, for example, the Ising model or the XY Hamiltonian. However, despite this simplicity, there are still a large number of open questions regarding, for example, phase diagrams, the dynamics, which is very hard when you increase the number of particles beyond 30 or 40, topology, the role of disorder or entanglement in these systems. And for these reasons, in the last few years, there has been really an explosion in the number of groups trying to map these problems into some other more controllable systems. And for that, there are many platforms around. For example, there are trap ions, superconducting qubits, Rydberg atoms, as I will show you just today. Ultra-cold atoms, quantum dots, and polar molecules, all of them provide really unique opportunities. And with this, I'm arriving to the outline of the remaining part of the talk. I will start with a few words about our experimental setup. In there, I will remind you the different type of interactions that one can have with Rydberg atoms. And then I will move to the main results that concern basically the quantum simulation of the Ising model on square and triangular lattices with up to 200 atoms. And then I will briefly mention some of the most recent work that we are doing that involves Floquet engineering of XX and Z Hamiltonians. Okay, so let's go to the first part. In our experiments, what we do is we use individual atoms trapped in optical tweezers. To do that, what we do basically is to focus very tightly a light bulb trap beam, you see here in red, and we do this using two spherical lenses that we put inside a vacuum chamber. With this, we can get trap volumes, as you see here, of around 1 micron cube, which is enough to trap a single atom. We can have trap depths of around 1 millikelvin. Now, to load these atoms in these traps, we are just using very standard techniques. We are just using a magnetic optical trap in which we can have a reservoir of atoms at around 50 microkelvin. And now the interesting thing with this setup is that the trapping volume is so small that two atoms just don't fit. What means is that during the loading, when a single atom enters the trap, nothing special happens, and the atom is just cooled down with the molasses light. But as soon as you have a second one entering the trap, both atoms undergo very fast light-assisted collisions that end up with both atoms being expelled from the trap. So this means that on the relevant experimental time scales, you can have at most one atom in each of the traps. And this is therefore a non-deterministic single atom source that has been demonstrated 20 years ago in the group of Philippe Granger at our institute in Palaiseau. Okay, so how can we know that? What we can do is to use the same mode light to scatter photons, and we can collect the fluorescence of these photons using an EMCCD camera. And when we do that, what we see is what you see here. This is a video. Basically, you see this white blinking dot corresponds to the fluorescence of a single atom in one trap. And then on the right, what you see is basically the trace over time of the signal, of this signal you see. So you see that there are two levels. There is the floor level, if you wish, that corresponds to 0 atoms in the trap, and another level that corresponds to one and only one atom in the trap. So with this, we know that we can have only at most one atom, and what we can do to know the occupation of the traps is to define a threshold. This is this red line that you see here, and then we can know if the atom is there or not. Okay, so this is all for single atoms. Now, if you want, of course, you want to do quantum simulation, what you want to do is to replicate these single traps and to have many of them. And for that, what we are doing is just using holography. We are using a spatial light modulator, and we imprint a phase in the dipole trap beam in such a way that we can create arbitrary light landscapes, if you wish, there. The important thing to realize is that the intensity distribution there in the focal point of the aspheric lens is just the Fourier transform of the phase that you put in your SLA. And with this, we can basically have many traps in different configurations, as you see in the video that is playing there. So again, what you see is that well, these atoms they are not at all, not all of them are at the same time in the traps, so the loading is non-deterministic. Still, you can take an average fluorescence image that has the appearance that all of them are filled, but this is not the case. And for some, of course, especially for quantum simulation, and for some time this was a problem, because ideally what you want is that all the atoms are filled, or at least that you have the same configuration once and again in such a way that you can collect some statistics. And after some time, a few years ago, we just solve it by just using an approach, a simple approach, which is just to rearrange the atoms in the traps. So what we do is just to overlap with our hologram another dipole trap beam, which is what we call a moving optical tweezer. This is basically what you see here, this more intense trap that you can steer in 2 dimensions, in up and down and left and right. And with this, you can do the type of moves that you see in the video that you can use to move, to grab an atom from one position and to move it along some trajectories that you define, and to release it in another position. Or you can even do more fashion trajectories if you want to, like you see here in a circle. Okay, so then the idea is that okay, at some point you stop the loading, and you take an image of your arrays. This is the image that you see here on the left, and now you ask your computers with some algorithm to arrange basically the atoms one by one into the desired configuration. In this case, is the picture that you take after on the right, in which it looks like a 1D chain, if you wish, with a shape of a snake. Okay, it contains more than 200 atoms. And very recently, we have updated our algorithms that allowed us, on the one hand, to do larger arrays than it was possible before. And at the same time, now we can really, truly do arbitrary geometries, in the sense that now the positions of these traps of the atoms can be really random, not random, but arbitrary, in the sense that you don't need an underlying Bravais lattice to locate these traps. And this is illustrated here with a pixelized version of a picture that we all know. And then as for the numbers, if you target 100 atoms, you can get easily filling fractions above 99%. That means that you have a probability of defect-free shots above usually 40%. And of course, this technique also works in 3D. You can basically operate the moving tweezer in the same fashion, just arrange the atoms plane by plane. but this is not what we are going to use here. Okay, so as I showed you, we can create these defect-free arrays that contain up to 200 atoms. In this case that you see here is a 14 times 14 square array. And the separation between these traps, these atoms, is typically a few micrometers, which means that the atoms are very easily addressable, and this can be used to manipulate the state of the atoms, and also you can measure the state in which the atoms are at the end of the sequence without crosstalk and so on. But of course, the problem is that atoms, if you want to do some kind of quantum simulation with interaction, that atoms in the ground state, they don't interact. So the solution to that is just to excite the atoms to Rydberg states. And Rydberg states are highly excited electronic states of an atom that has, they have typically quantum numbers, principal quantum numbers between 50 and 100, and they have very nice properties. I don't want to go into the details, but I would say that they have two very nice properties for quantum simulation. On the one hand, they have large transition dipole moments, scaling as the principal quantum number square, and also they have a relatively long lifetimes, exceeding hundreds of microseconds or so. And these two properties allow for the quantum simulation of complex condensed matter systems on a very different and also more convenient length scale and also time scale. Because you see that for distances of a few micrometers, one can get easily interaction energies of a few megahertz, which means that the interaction time, or the time in which the dynamics takes place, is on the microsecond time scale, which is still much smaller than the typical lifetime of the Rydberg states. Okay, and now for Rydberg excitation, we are using, in the past we were using a very standard scheme. It's a 2-photon excitation of resonance through this intermediate state of 5P that you see here. And very recently we have updated, upgraded the experimental setup and use now what we call an inverted scheme, because now the infrared laser is in the upper transition, which allows us to get more radio frequency, more power basically in this type of laser. And at the same time, we gain as well because the technology of the lasers they have less noise. All right, and with this we can you can forget about the details, and basically you can imagine that you have an atom with two levels, the ground and the Rydberg level, that are coupled by a laser field with radio frequency omega, and then you can drive basically radio oscillations between the ground state and the Rydberg state, as you see here, where we have improved the coherence time by factor 20 with respect to the experiments that we used to do before with the old excitation scheme. And then for the numbers, the Rydberg excitation probability for a pi pulse, this is to say here, is if you take the raw data, is around 97%. If you correct with a small detection errors, this goes to 99%. Okay, and now for the interactions, there are different types of interactions that you can have when you have two Rydberg atoms. Perhaps the most well-known type of interaction is the van der Waals interaction. That is just a diagonal shift in the coupling matrix. This happens when you have two states, two atoms with the same state, NS, NS in this case. And basically the effect of the interaction is to shift this doubly excited state. Okay, this type of interaction can be used to engineer a quantum Ising model, because the type of interaction, this diagonal interaction, is sigma z type of term if you look you express this in terms of the spin language. But there is also perhaps a less well-known type of interaction, that is the resonant dipole-dipole interaction, which happens when instead of having two states with the same parity, now you have two states with different parity. And in this case, I call them NS and prime P. In this case, the effect of the interaction is basically to exchange the excitation between S and P. So if you have one atom in S and the other one is in P, then the interaction flips the excitation, and then finally you will have P, one excitation in P, and the second one will be in S. And with this, it's a flip-flop kind of exchange Hamiltonian, and then you can engineer what we call the XX model. All right, so we are going to the second part. I will show you some recent results. And yes, we will first exploit these van der Waals interactions to create this Ising Hamiltonian. So perhaps the most well-known interaction effect with van der Waals interaction is the Rydberg blockade that you all know about. So this is just a quick reminder. So when you have one atom with two levels, the ground state and the Rydberg state, coupled by this laser field of radio frequency omega, nothing special happens. But as soon as you have two of them, the effect of the interactions is to shift this double-excited state out of resonance with your light field. This happens usually below a certain distance. That is what we call the Rydberg blockade radius, in which case you can no longer, if you tune your laser to have a single photon resonance, you can no longer excite the two states at the same time, but instead you couple to the symmetric combination of these two states, down, up, up, down, which contain single excitation. And this is, by the way, an entangled state that has been the origin of many proposals in the early 2000s to build, for example, gates and so on. And the other signature of this effect is that the radio frequency, when you couple to this symmetric combination, is enhanced by a factor square root of 2 or square root of n if you have n atoms. And this is what you see here, basically in blue, is the same radio oscillation that I was showing you before. And now I show you in purple the radio oscillation that corresponds to this symmetric coupling, where you see that the frequency is enhanced by a factor 1.41. Okay, now the interesting thing here, if you look at many of the physics, is that the Hamiltonian describing the evolution of the system is just a quantum Ising model. To realize that, the only thing that you have to do is you can just map your own state to a spin down, if you wish, the Rydberg state to a spin up, and in this case, you can recast your Hamiltonian in terms of this quantum Ising model, where you see that you have a transverse B field that is proportional to your radio frequency omega, and you see here the Pauli matrix sigma x. Then you have a longitudinal field proportional to the detuning from resonance of your laser, as you see in the scheme here on the right. And finally, you have the spin-spin interaction term that is proportional to Ni Nj, which is the occupation number of the atoms in the Rydberg state, which means that you will only have interactions if the two atoms are in the Rydberg state. Okay, so now just to illustrate how you go to this from this Rydberg blockade to simulate antiferromagnetic order, you can just imagine that you have a square array where you can put the atoms. This is tunable in our experiments at a separation A, and each of the atoms have two levels, the ground state and the Rydberg state, up and down, if you wish. And now what you can do is to tune the parameters of your Hamiltonian in such a way that you just select this Rydberg blockade radius that covers first neighbors. Okay, so in this way, once you place an excitation, a Rydberg atom here in dark blue, there, it's not possible to create any other excitation in this circle that you see here of radius RB. And now you ask yourself, what is the densest packing you can get, provided that you don't have to apply any energy cost, following this condition. And the solution to this is that, this type of staggered configuration or checkerboard pattern in which you have one Rydberg excitation every second cycle. And this is the antiferromagnetic ground state that we are trying to look for. And of course, you also have the complementary solution because you have a degenerate ground state. Okay, so it turns out that this problem can be more generally described with a phase diagram in terms of the transverse B field that, remember, is proportional to the radio frequency omega, and the longitudinal field, which is proportional to the tuning from resonance of our lasers. This phase diagram has two regions: the paramagnetic region, in which the spins basically follow the magnetic field, and there is another region. This is the antiferromagnetic region, which is the region in which we are interested. And these two regions are separated by, in the case of the square lattice, by a second order phase transition. So then the idea is that we want to basically prepare the antiferromagnetic state there. But we will start with all the atoms in the ground state. So the idea to do that is to use this idea that one can connect the ground state in the two phases, provided that you vary very slowly the parameters of the Hamiltonian in such a way that you will always be in the instantaneous ground state of the system. So what we are going to do in these experiments is that we will start with all the atoms in the ground state. We will turn on our laser with radio frequency omega, then vary the detuning, as you see here, and then finally switch off the lasers. Okay, and then eventually we will try to prepare this the ground state in the antiferromagnetic. Okay, so we do this for a 10 by 10 square array. So this is the initial configuration, as I showed you before. It's a defect-free array. And now we apply the sweep. And what you see on the right is that there are some atoms that are missing in a kind of a staggered configuration, which is the thing that we are looking for, because actually the atoms that are missing, that you don't see in the image, are atoms that have been promoted to the Rydberg state. And this is so because in our experiments we cannot detect atoms if they are in the Rydberg state. Okay, so this is very visual because you can see when you are performing the experiment, you can see the images live in the screen of the computer. But unfortunately, this does not happen very often because in these cases you see one shot in every 500 or so. I cannot show you the histogram, the state histogram for the 10 by 10, but I can show you the histogram for the 8 by 8, and then you can see that out of the 10 to the 19 possible states, there are only 2 states coming out of the noise that correspond to these nail configurations, the 2 antiferromagnetic ground states of the square lattice. And there have been other works in 1D and also in 2D, in the group of Immanuel Bloch and the group of Looking. And also we did some work, but now this, with the new excitation scheme, this is much better. Okay, so another quantity that we can look at is the pair correlation function, which tells you basically what's the probability to find an excitation at position K, provided that you have already another excitation at position L. So positive correlation when you have 2 spins up, and negative it is 1 up, 1 down, and then what you see basically is the same kind of a staggered pattern. It tells you that what you prepare is very close to the ground state of the system. And still, the correlation function is not homogeneous. It's slightly decayed, and you can see that you can fit this correlation, this decay, with a correlation length, which in this case it's around 9 sites, which basically tells you that this is covering the full, almost the full array, the 10 by 10 array that we have. Okay, so we can do the same thing with bigger arrays. In this case, we didn't manage to get a perfect shot, but we can very easily find bigger clusters, like in the one that I'm showing you here. In this case, 181 atom antiferromagnetic cluster that we can prepare for win this type of sweep. And as I told you before, because we think that especially for quantum simulation, it's very important to study the dynamics. We wanted to know what we are doing really when we are doing the sweep. So the idea is, in this case, is we ask our colleagues, with 30 colleagues, to do the full simulation of the process. And what we are going to look at is what we call the staggered magnetization, which is an order parameter for this type of system. And this staggered magnetization is basically you can divide your lattice into sublattices A and B, and then you plot the occupation in A minus the occupation in sublattice B. And what we are going to do is to show this staggered magnetization as you basically are performing the sweep. You will stop the sweep at certain times, and this is what we observe here by the curve. So these are the points, the blue points that you see here, as a function of the time of the sweep. And you see that the theory in which you include all experimental imperfections that we can really calibrate independently, the interaction energies, the radio frequency, the detuning, or even the finite temperature of the atoms, matches very well with the results of the experiment. The same is true for the case of the 10 by 10. As you see here, between the blue points and also the black line. This curve, it tells us also that our experiment is performing well, but it's not perfect, because otherwise, if it was perfect, what we should observe is the yellow line that you see here. So this is quite encouraging. Okay. Another important thing to say is also that we are reaching the limit or the point where numerical simulations are very challenging, because already to get the results that are illustrated in this graph, it takes 10 days of MPS simulations.
Can I ask one question?
Sure.
Yes. Why are you doing this in the delta omega phase parameter? Because it seemed curious to me. Why are you using this way? Because instead of this, you could use just keep a point of omega fixed and then increase delta. Why are you doing this of keeping delta fixed, then increase omega, then keep omega fixed, and then?
Well, the reason for that is that I mean, there are many ways to cross the phase transition, if you wish. The energy gaps at the phase transition are not equally around the border, so it means that the gaps are smaller if you cross basically there horizontally. So the gaps, you want ideally to be adiabatic, you want ideally that you cross this gap. I mean, the gaps are the biggest possible, and this happens basically at the top of this dome. So then, as for why we are doing straight lines, basically, this is just a simple approach, experimental approach. But in principle, you could basically optimize these parameters, and you can really come up with other type of ramps that perhaps give better fidelities in the end.
Okay, thank you.
Okay, so more recently we have done the same type of experiments, but in this case with a triangular array. The phase diagram looks a little bit different because now we have two different regions with 1/3 filling and 2/3 fillings, as you see here. So the idea is to do the same. We start in the paramagnetic state with all the atoms in the ground, and we try to enter these two regions. So here I show you again the staggered magnetization. This in this case the triangular configuration, there are 3 sublattices. So I just plot this thing in the complex plane with using this expression. And what you see basically here is in blue are the points that correspond to the experiment, where you see a triangle that points to the right positions, or correspond to 1/3 filling. And I have divided this hexagon in 2 parts. Just to show you the results of the simulations in which you include the experimental imperfections, and you see that the degree of agreement is quite good. And then on the right, you can see some of these almost perfect clusters where you have the 1/3 filling. And of course, then you can do the same thing, but in this case, you can try to enter the 2/3 region. And what you see is different from the 1/3 case. And you see that now you have a triangle in the staggered magnetization, but points to the right direction, corresponding to 2/3 filling. And also you see that the agreement with the theory is quite good. Okay, so of course now the interesting part that we are willing to explore is what happens at 1/2 filling, because there is when you are expecting to see to have a geometrical frustration that play a role in the system, and we would like to see also what happens there, what we call, or the theorists call, the order by disorder phase. But for the moment, I cannot show you any results on that. We need to improve a little bit the experiments to be able to see that, but we are working on that.
Daniel, can I ask you something?
Sure.
It's a bit about the theory, because I'm a bit surprised. So you do experiments with MPS, but you are like doing this kind of approach where you express the 2D system as a 1D chain or something like this?
Sorry?
No, I was wondering, because MPS only work for one-dimensional system. You have a
Yes.
one. Do you know how do they manage to deal with the 2D system?
Well, I guess it's the you in principle is 1D, but you can engineer the different couplings not to have
Okay.
the second dimension. Yes. Yeah. I don't know really the technical details. I know that they are not using PEPs or other methods because MPS. It seems that this is computationally less expensive, I would say.
Yeah, I
But,
see. Nice interest. I think I would say they are going to have a hard time to simulate the order by disorder with one-dimensional MPS because it's a very delicate phase that has strong 2D correlations. But, well, I guess this is where the quantum simulation is going to be really exciting, right?
yes, yes, yes. I totally agree. Yes. In addition, it's not from what I understood, is still not totally clear what you should observe.
I see.
This order by disorder phase, or if you, I mean, it's a little bit unclear because it seems that at this in this gray region that you see here, you are expected to see some additional phases, but
Yeah.
and it's not fully explored, both on the theoretical side and also experimentally. Let's say that.
Yeah. Well, there were some people doing Monte Carlo simulations who came to the conclusion that you could observe spatial correlations that were special in this phase, but I can tell you later if you want. So.
Okay. Yeah.
Or maybe you know already. Just
Okay. Okay, thanks. Okay, so this is it for this part with van der Waals interactions, and now I want to show you some preliminary data, some preliminary results that we are doing on flow K engineering of different Hamiltonians. So for now, you can just forget about van der Waals interactions, and now what we do is to promote the atoms, all the atoms to Rydberg states. But in this case, we have if you have what you can do is to have two different Rydberg states with different parity, S and S state and a P state. And now the coupling is not done with a laser, but is done with a microwave field. And then, but it's still the same. You can drive coherent Rabi oscillations between these two states, the S and the P, as you see here. And as for the interaction, then it's a little bit also different. In the two atom picture, basically you can have the two atoms in the with the spin down, the two atoms in the spin up, or you can have this basically super radiant and subradiant state that are separated by this interaction energy scaling as 1 over r cubed. And with this is type of flip-flop interaction, you can engineer the X model. And something that has become the specialty of our group is to do this type of coherent spin exchange oscillations. In this case, what you do is just with two atoms, you just prepare one atom in S, the other atom in P, and then you see this coherent exchange of the oscillations between S and P. But this is out of phase, as you see here. So there is no driving, there is nothing. It's just you prepare the atoms and then you just let them evolve. And since this state up down is not an extent of the system, they just exchange the states, okay, with this interaction energy. Okay, so with this we have recently studied a few things, like for example topology, many topological phases 2 years ago, and also we have implemented density-dependent pairs phase. But I'm not going to speak about these experiments today. But the interesting idea now is that, as I showed you, I have just presented, you can use two naturally implemented Hamiltonians and the quantum Ising, just using van der Waals interactions on the one hand, and you can use dipole, resonant dipole interactions to engineer the XX model. But ideally, what you would like to do is to really engineer something more generic, and in particular, you would like to have access, for example, to the Heisenberg Hamiltonian, in which you will have basically the two things combined, and you would like to have also the sigma z term, or also the XX z Hamiltonian. There is a particular case of the other Hamiltonian. Okay. So what we want to do then is to use, the idea is to use this XX model, which is naturally implemented in our platform as a resource Hamiltonian, and do periodic driving with the microwaves to engineer this other Hamiltonian. So the way we do it is that well, we can use this external microwave field which has this radio frequency omega and phase phi, and then when you write your Hamiltonian, you can see that basically what this microwave field does is you can do arbitrary rotations along sigma x and sigma y. So with this, you can basically transfer your interactions to a different plane, if you wish. And this is what we are going to try to do now. So this is some work that we do in collaboration with the group of Matthias Weidemüller in Heidelberg. So they are successfully applied this approach to an ensemble of atoms. And now the idea is that we do the same thing basically with an array. So the idea is just to use this Floquet sequence, which is a sequence that is borrowed from NMR experiments. You see that there are 4 pulses, 4 pi/2 pulses on the microwave, in which you rotate along x minus y, y, and minus x. So the idea is that initially, for a time tau1, you let the system evolve initially with your xy Hamiltonian. Then when you perform the rotation of pi/2 along x, what you do basically, if you wish, is just you are rotating your spin operators, and then you transform your Hamiltonian in a xz Hamiltonian that evolves during this time tau2. Then you apply another pi/2 along minus y, that then allows you to have this Hamiltonian along yz, and this you roll for some time as well, and then you basically undo what you have done before. So this, if in the case of that these pulses are very short, you can think that the time for the complete sequence is twice tau1 plus tau2 plus tau3. And this procedure, of course, you can repeat it many times, as many times as you need to follow the dynamics. And this in the limit in which the interaction energy times Tc is much smaller than 1. What you can do is to basically convert the time-dependent Hamiltonian into an average Hamiltonian, in which, when you do the math, you see that basically you have now 3 terms, and you have an additional term that you didn't have before, which is depending on this delay tau2 plus tau3. And what this is basically the type of programmable Hamiltonians that we can have that are very nice, and we didn't have access to them before. Okay, so just to demonstrate this thing, what we are going to do is just to take a particular case. In this case, we are going to fix tau2 equal tau3. And with this, we will have access to the xz Hamiltonian. And we will define this anisotropy parameter in this way. This anisotropy parameter can take values between 0 and 2. And this is then the Hamiltonian can be written as you see here, where basically you have the terms xx and sigma z, sigma z, sigma y, sigma y, sorry. And then you have an additional term with this factor in front, okay, which is the one that we can vary as well. Okay, just to demonstrate as a proof of principle how it works for 2 atoms, what we are going to do first is that to see what we could do is to prepare the 2 atoms along y. To prepare that, what we do is to do a pi/2 rotation along x, and then when you expand basically your state, you realize that you have 3 terms. The first 2 terms are eigenstate at 0 energy, and the third term is an eigenstate at 3/3/R3. So this is again for the natural implemented Hamiltonian xx. Okay, so when you just measure the magnetization along y, what you are expecting to see is an oscillation, as we have measured, of at the frequency of the eigenstate, basically that oscillates between 1 and -1. Now what you can do is to just to demonstrate how it works. You can let the system evolve for some time, as we did there, in which case the red points basically coincide with the previous experiment. And now in this gray region here, what we do is to apply this coherent periodic drive. And what you are expecting to see in this case, if you prepare the xsx, is that in this case the 3 terms that you saw before are eigenstates. So in which case the system should not oscillate. So the dynamics should be frozen in this case. And this is what you see here, that we have stopped basically the evolution or the oscillation along y. And then as soon as you stop the drive, you see that you can recover the oscillation that corresponds to the natural implemented Hamiltonian. Okay, and of course you can vary this delta parameter to have some other values. And in this case, what you do is you can see here in red is that then you can slow down the magnetization oscillation if you wish. And we have done this for different type of values of delta, and then we see that basically it fits very well what is expected from basically the theory. Okay, so another thing that we can do, as I told you before, as we can the specialty of our group, is to prepare one atom in up, the other in down. In this case, you will see this spin exchange excitation. I'm only showing the probability to have up and down. And when you apply the drive, you let the system evolve for some time. When you apply the drive here, and it corresponds to the red curve that you see here, you see that the oscillation gets slower. And this is because basically the interactions terms that you have initially in the first two terms, you have moved this part of interaction to the third term, in which case what you are expecting to have is that you are expecting to have a reduction of the interaction energy by a factor of 2/3, which is just what we are measuring right now. Okay, so this is just the thing that I can show you for now, because now what we're going to do, of course, is to try to scale up the system. We want to go to a many-body implementation of this to see how it scales and how easy it is to perform experiments with this technique. And with this, I'm arriving to the end. I hope I could convince you that this platform is a nice platform in which you can have a single particle resolution addressing. That currently we can use more than 200 atoms in arbitrary geometries in 1D, 2D, and also, if necessary, in 3D. That we can have tunable interactions, and now we can have another tool in the toolbox, this flocking engineering, and that can be used to implement many Hamiltonians. And then finally, as future directions, there are many directions that we can explore. But in principle, we are going to follow two different routes. On the one hand, we are going to explore topological matter in 2D. This is some collaboration that we have with Hans-Peter Büchler in Stuttgart. And also, as I told you in the presentation, we would like to observe these frustrated phases, this order by disorder in the quantum Ising model for triangular or frustrated lattices. Okay, so this is everything that I wanted to tell you. Thank you very much.
Thanks, Daniel,
for
the very pedagogical presentation. So are there more questions?
So I have just one stupid question. So do you have timescales for two interactions, C6 and C3?
Sorry?
You have timescales for two interactions, C3 and C6, the
yes.
change and the Ising type. Do they differ a lot? Because I didn't remember the numbers from the plots.
Well, the difference, let's say that you can get, usually the C3, I mean, the dipole-dipole interaction is stronger for typical quantum numbers that we are using. Just to give you a rule of thumb, if you target Rydberg states around 60, you get, we are speaking about the distances, you can get, to get the same interaction energy, you will need, in one case, in the case of van der Waals, you will need to fix the distance around 6 micrometers or 7 micrometers, whereas to have this dipole-dipole interaction, you will have to have at least 12 or 15 micrometers separation. But this, of course, then is a different scaling, and it will depend on the specific Rydberg state. But when you are dealing with dipole-dipole interactions, the problem that we have usually in our experiments is that the array needs to be large. It's not. I think it's a problem because it's a technical problem. The technical problem is that it's the power of the lasers, because the beams are global beams that cover the full array. And of course, ideally, what you want to have is something that covers the full array totally homogeneous. But in practice, we have Gaussian beams, and yes, you have Gaussian beams that are, let's say, 200 microns with a waist of 200 microns or so. And then, yes, ideally, it's much better if you use with van der Waals interaction, you can pack these 200 atoms, if you wish, with 10 microns. And this is fine with our acetation lasers. Now, if you want to do the same experiments with resonant dipole-dipole interactions, you have to have maybe a factor 2 in the distance, and then you cannot really have as many. Just to give you an example for what we are trying to do now with these resonant dipole-dipole interactions for this flow key engineering, is to have a 1D ring, a 1D chain with periodic boundary conditions. And now we were just this morning we had a meeting to see what we were going to target for the experiment, and we can target at most maybe 20, because otherwise the ring gets too big and it's going out of the excitation beams.
Nice. And also in the beginning, when you were doing these adiabatic passages, there were some imperfections.
Yes.
Are they related to the phasing, the decay of the atoms, or do you have any identification of what can be going there, or is it just the gap, the size of the gap and the speed of your passage?
There are different things. So basically, the experiments that we did 2 or 3 years ago, we had done this. I am not going to say that it was the same experiment because we saw different features, but we tried to do the same experiment with the square and triangular lattices with the old excitation scheme. And in this case, what we saw was that the experiments were basically limited by the phase noise of the lasers. Because, it was not much in the theory when you were putting the experimental imperfections, and then we realized that, you could see, if you look basically at you remember the histogram that I was showing for the preparation with the 2 peaks. If you compare the experiments with the PRX publication that we had in 2018, I think it was, you could not see any peak coming out of the noise. So now with the new excitation scheme is much better because the lasers are titanium sapphire lasers, so they don't have phase noise at the frequencies around 1 megahertz or 2 megahertz. This is the typical radio frequencies that we have, but still it's not fully working. So there is one part, as you said, that of course you cannot really even do adiabatic preparation in the sense that for a finite system you will have the gaps will close, and then you will need an infinite time to prepare adiabatically the state. But it turns out that based on the simulations that they have done, this is not the limiting thing, because you can get really very high fidelities still in the preparation. And the problems that we have from the experimental point of view is more related not to the noise of the laser, but now is the finite temperature of the atoms. Because the atoms, we have the atoms in the optical tweezer, and these atoms usually in the transverse direction they don't move a lot. It's maybe the spread is a few, perhaps 100 nanometers, so it's not much. But transversally they can move because they are not very confined. They can move even depending on the temperature. They can move even 1 micron or so. So it means that it's something that I didn't say during the talk, but the way we do this experiment with the Ising Hamiltonian is that we initially prepare the atoms, all the atoms in the ground states in these tweezers, and just to avoid light shift, what we do is to switch off the light. So when we switch off the light, do the excitation and everything, because the Rydberg atoms are not trapped, the atoms are in free flight, and we have a low temperature. Typically, we have temperature of 10 microkelvin or so, but it means that during the time scale of the experiment, they still move. And this movement is not the same for every configuration. And what means is that in the end, when you average out everything, then it leads to basically a reduction of the good Nell state that you are going to prepare. And this is actually what we're working at right now in the experiments, because just with Andreas Losty and his team, they said, okay, first of all, we don't know exactly what you are supposed to see, but it's very difficult. We are just in the edge in which, it's just a matter of temperature. If you could reduce the temperature by a factor 2 or so, then you could see clearly features that are very interesting. But for the moment, we are just in this case, and we are trying to, this summer, the plan is to implement Raman cyber cooling on the arrays to reduce the temperature of the atoms even more.
Nice, very nice explanation. Thank you, Daniel.
Yes. some other question?
I have one.
Okay, I want to ask. Okay.
Yeah.
Ricardo?
So I was wondering, actually, it's along the same lines. So right now, what you are doing is trying to prepare adiabatically the ground state. But will it be possible to reduce the rate at which you cross the phase transition and then basically look for the confirmations of the QUINFOG mechanism or scaling laws, critical exponents, and so on?
Yes.
Have you thought about it?
Yes. Actually, yes. Because this is something that the group of Misha Lukin did in 1D. There is a paper about this QUINFOG experiment. I mean, when you measure basically all these exponents, critical exponents, and we have even tried to do it in our experiment, just doing the simplest, the same simple approach as they did in the group of Lukin in 1D, but it turns out that it's not exactly as easy, because you need to take into account the dynamics and you need to take into account basically the parameters, because and it's not even clear what they did that is so robust, because we had tried to reproduce the results of them and we managed to reproduce it for 1D to reproduce the results, but this depends slightly on the parameters. So yes, this is another possibility, and of course it's interesting, but it's a little bit delicate. And the solution to this is that perhaps this one idea is that also with the team of Andreas, that we were saying, okay, maybe perhaps we can do the simulations to see what is the good window of experimental parameters in which you can really have access to these critical exponents, for example. And in this case, you could do it in 2D, for example, which would be interesting. But yeah, basically the short answer to this is that we have tried to do it because we thought it was simple, but it's not as simple.
Okay, yeah, I can see that. Okay, thank you.
Okay. If not, maybe I want to ask a last one. So, I mean, about this outlook, about this 2D topological matter. So, what type of model? So, it's kind of honeycomb Haldane-like model, or?
Yes, it's to see its states in a honeycomb lattice.
Okay, so it's really okay.
So this is a little bit the idea. The idea is that you can it's a little bit the same experiment that we have published to engineer this spiral space. And you can use basically this resonant dipole-dipole interaction to engineer this phase-dependent phase, in which you use basically the degree of freedom that you have in the interaction, because then you can couple states with different angular momentum. And since in the end you have to match in the dynamics, you need to match basically the change in the internal momentum with you need energy conservation, then the excitation will propagate along the edge. And this experiment is something that we actually, this collaboration started like in 2015 or even before. It was when I started in the lab, and we have not done the experiment yet. The plan was to do it also this summer, but yeah, I don't know.
No, it looks super cool. Okay, so are there more questions? Well, if not, thanks, Daniel, again. It has been very nice, actually.
Thanks to you.
Yes. Let's hope we can meet sometime. COVID after.
Thanks to you.
Yeah.
Okay.
Thank
Bye.
you.
Thank you. Bye.
Bye.
Bye-bye.
Bye.
Thank you.